Bismillah ar-Rahman ar-Rahim. Today's lecture is lecture number 13, the unsteady flow equations. This is the unsteady flow equations. Contents. We're going to take the basic equation of transients. We're going to take the method of characteristics, partial differential equation, and the method of characteristic, the characteristic equation for unsteady pipe flow, their solution using finite difference approach, initial condition, boundary conditions, valves, dead end, reservoir, etc. Many boundary conditions will be discussed. To remember, in waterhammer analysis in 1963 has been solved by a graphical method. The major or the most famous book was made by John Parmaki in 1963. This is the cover, and I have this book with me. This is the first book I learned or studied to learn the waterhammer, and we learn how to draw the problem. The problem may take 2 hours or 3 hours to solve one small, simple case. So now, thanks to God, we have a computer program that can solve the problem in seconds. The other major book which we have, which is called Applied Hydraulic Transients by Chaudhry to 2014, we're going to study chapter 2 and 3 from that book. And also the other book which I like also, which is Hydraulics of Pipeline System by Larrock and Jepson and Waters in 2000. This is, I think you have that book with you. I'm going to study chapter 8 and 9. Okay? The same chapter 2 and 3 and 8 and 9, they are synonyms. Yani either you study from here or there. You don't have to study both. But this is your reference, our reference during this lecture. Basic equation of transients. So during transient, we have pressure and velocities. In pipe varies with distance and time. Again, we have pressure and velocity, and both those two parameters here are varies along the pipeline, along the distance and time, with respect to distance and time, x and t. However, they follow the laws of conservation of mass, اللي هي اسمها continuity equation, and the conservation of energy, اللي هي momentum equation. I guess you have passed through continuity and momentum before, but now we're going to see that in a different shape. Before we start the equation, we need to know the assumption. And I summarize the assumption in this page. Don't worry about that, but it summarizes everything I need to say about the main assumptions, which is considered in the basic waterhammer equation. This has been done by Covas 2003. There is 3 assumptions regarding fluid, flow, and pipe. Regarding the fluid, it is one-phase flow, means it is liquid. There is no gas there. It is homogeneous, compressible, and the elastic wave is considered there. Change in fluid density and temperatures are negligible here. Okay, the change in density with temperature along the liquid is negligible. Okay. In the flow assumption, the flow is one-dimension flow, and also the head losses. The major point here, we are using the head losses term as a steady state friction formula. And we're going to learn what is the meaning of steady state friction formula here. Remember, in recent research, the steady state friction formula cannot withstand when you have a very fast transient. So more advanced formula has to be used there. With respect to the pipe assumption, the pipe material is linear elastic behavior, dynamic بتاع الفلويد pipe interaction اللي هي structure, fluid structure interaction ده مش موجود معنا. We don't have that into consideration. And the pipe is straight and uniform and all that stuff. So this is the major, I summarized all the assumption for you, at least to know what we are going to talk about during this lecture. But let's start with the basic equation of transient. Continuity equation, the applying law of conservation of mass to the control volume between x1 and x2. This is the general formula, integration from x1 to x2. If we have a control volume along the liquid, we have the partial by partial t. Rho is the density multiplying by a dx, rho av at 0.2 minus rho av at 0.1. By applying Leibniz's rule here, the first term can be divided throughout by delta x. I can divide everything by delta x here. So this term here will be transferred to partial by partial t rho a. And when I divide rho av minus rho av over delta x, I can write down this as partial by partial x rho av. Okay, remember this, we are dividing this through by delta x as it approaches to 0 here. So this is a term from this equation to this equation. This is what we have here. If I expand the two parameters here, if you look, you will find that partial rho a by partial t, you can expand things and get this into that formula by saying 1 over rho d rho by dt, 1 over a dA by dt, and this is plus partial rho v by partial x. If you divide all the equation by rho a, if you take it out, you will find this formula, and these two terms, the first term and second term, is this expansion of expanding, we're arranging a term and we're saying partial rho a by partial t. We have the continuity equation in this form: 1 over rho d rho by dt, 1 over a dA by dt, partial v by partial x. The problem we have here in this equation is two problems. The problem number one is that the derivative of the density with respect to time, I can say it's impossible to be evaluated. You cannot evaluate the change of the density with respect to time, especially when you have a transient analysis here. And also dA by dt. Can you imagine? You want to know the change on the area, cross-section area with respect to time. So if I ask you to, can you get to me the change of the cross-section area with respect to time, this is impossible again to find out. So what we're gonna see in the next slide, how I'm gonna substitute the first term here and the second term here with something I can evaluate, something I can measure. The first part we're gonna talk here, we're gonna talk about the bulk modulus of elasticity. We all know that the K, bulk modulus of elasticity, is equal to dP by d rho over rho. Okay, the change of the pressure, the change of the density over the density. So I can arrange by saying d rho equal to rho over K dP. If I take the derivative from both sides, so it will be d rho by dt, rho over K dP by dt. So if I arrange, I get the rho on the other side, the left side, so it will be 1 over rho d rho by dt, 1 over K dP by dt. Now, thanks God, I have the first term has been substituted, which is 1 over rho d rho by dt by something I can evaluate. I can 1 over K dP by dt. I can evaluate, or I can measure the change of the pressure with respect to time. So the first assignment has been done here. I switch, or I change 1 over rho d rho by dt with something I can work with, 1 over K dP by dt. Now let's go to the other part. Remember, the other part is 1 over A dA by dt. So first we have the area, which is by r squared, which is where r is a pipe radius. So if I have the derivative with respect to time for both sides, it will be dA by dt, 2 by r dr by dt. Okay, so if I can say, I can multiply by, for the right side, I can multiply by r, 1 divided by r, it's the same thing. So it will be 2 by r squared 1 over r dr by dt. So again, 2 by r squared is a, so I can keep it as 1 over a dA by dt. It will be equal to 2 multiplied by 1 over r dr by dt. Okay, remember the strain term is defined as dr over r, dr over r. So I'm going to take dr over r by putting this instead by d epsilon. This is the strain. So the same value of 1 over a dA by dt equal to 2 multiplied by the derivative of the strain with respect to time. Again, I need to have something easy to measure. So I need to substitute with the Hooke stress. In the Hooke stress, we have epsilon equals sigma over Young modulus E. And we know that sigma, again, we know that sigma is equal to P multiplied by D over 2E. P is the pressure intensity multiplied by the diameter, pipe diameter, over to the thickness of the pipe. So using those two equations, I can substitute epsilon by P D over 2 small e capital E, which is Young modulus. Again, I'm going to go to that expression of d epsilon by dt by taking the derivative for both sides with respect to time. It will be d epsilon by dt, d equal d over 2 thickness E, Young modulus E, dp by dt. Okay, so now I have this term substituting the strain with something I need to look at, which is this one. So I'm going to take this term from this equation and substitute this term instead, which is here. So it will be 1 over a dA by dt equal to d over E, capital E, which is Young modulus, dp by dt. Now I succeeded to replace the two difficult term, which is 1 over a dA by dt, and the other term, which is 1 over rho d rho by dt, by 1 over k dp by dt and d over ee dp by dt. I have to return back to the continuity equation and substitute those two terms in their place here. So I will find out that partial v by partial x equal to 1 over k, 1 over ee dk dp by dt. When I look to that equation, surprisingly, I find this term, I have partial v by partial x dp by dt. I have this term. When I look to that term and I arrange that term, it will be and make the inverse of it. It will be k over rho 1 over kdE over ee. People who look to that term with this units and dimension of that part, they find out that this is called a square. They find the dimension analysis for that term, it's equal to L square over T square, as if it is a speed. If you get the square root, of course, if you get the square root of a square, it will be a. So you will find that the dimension of a, it will be length over time. And as a result, they call it a wave speed. So people, they find out that this term, it's L square over time square. So the square root, it will be length over time. And that's the reason they say that this is called a wave speed. If you notice that this is the wave speed which we have studied with a certain lecture, a specific lecture earlier in our course here. So if I put a square on that place here and I arrange and I took out the dp by dt by expression, if I have dp by dt, it will be partial p by partial t, dx by dt, اللي هي v, multiplying by partial p by partial x, and then the third partial v by partial x will be here, and you multiply by the a squares. So this is the formula of continuity equation here. So at that slide, the advantage which we have here, number one, we took out the term of the derivative of area with respect to time. We replaced the term of the d rho by dt, and we put everything in as a function of pressure and velocity with respect to x and t. This is called the continuity equation, or that simple expression for it. Remember, we all know from fluid mechanics that P, pressure intensity, equal to gamma H, so equal to rho G multiplying by H. So looking for P here, if I take out P and put instead rho GH and arrange, so I can write out, this is the equation of continuity again with H, and this is, I wrote down here the momentum equation on this form, which you can find the F, which is friction, Darcy-Weisbach friction factor, and V and V, and the two column here saying that this is without sign, without even plus or minus, so you can put this form to give you the indication of the sign of the velocity. If I put V squared, so the V squared, if I have the V with minus sign, it will disappear. By putting this by this form, it will show the sign of the velocity because this will be without sign. Now, the general equation of motion and continuity, the first one is the momentum equation, the second one is the continuity equation. Now, we're going to ask ourselves what to do with those equations, how I can solve them. This is partial derivative. I cannot have any numerical technique with partial derivative unless I transform that into an easy way to solve. This is what we are going to learn in the next slide. This is the basic equation as we put. Remember, there is a term here called V partial V by partial X, and here there is a term called V partial H by partial X. To make it more simple, the convective acceleration, those two terms, I'm going to take them out. They are very small with respect to the other term, and we can take them out and have the simple equation of momentum like this, and the continuity will be like this. Those are the two equations which we're going to live with them for the rest of the lecture. This is the momentum, and this is the continuity. Now we're going to find out a method to solve this equation. We start with saying the method of characteristic. Method of characteristic, it's an easy way to handle the partial differential equation and try to make a total derivative for it. How to do that? First, we have two terms, which is called velocity and pressure head. We're gonna call a name for the equation. Equation number one, I'm gonna call it L1. The momentum equation, I'm gonna call it L1. And it's still equals 0, of course. And the equation of continuity, I'm gonna name it with L2. So nothing wrong with that. So this is L1 and this is L2. Remember, all the parameters here, you know them. You know the bulk modulus K, you know the density rho, you know your Young modulus E capital, and you know the wave speed, which is square root of K over rho, 1 over KD over EE. So now, after naming the equation, we need to do some manipulation here by take a linear combination of L1 and lambda L2. What do you mean by that? The equation L2, I'm going to multiply it by a multiplier called lambda. We're going to learn what's a lambda what the meaning of lambda here. But first, I'm going to create a new equation, which is, we name it L. I'm going to name this L, which is equal to L1 plus lambda L2. Again, to remember that, this is called lambda, no, this is called L1, this is called L2. What I'm going to do right now, I'm going to add L1, and then I'm going to multiply L2 by lambda and add it to the first one. This is simple adding things, linear addition, linear combination. So L1 plus lambda L2. This is called L1, and this is L2. I'm going to multiply it by lambda. Nothing wrong with that. I'm going to arrange here. I'm going to take all the H's together. I'm going to take all the v's together. I'm going to keep the friction factor alone. Again, this is arrangement. If you look to that, I have partial h by partial t, g over lambda, partial h by partial x. Again, partial v by partial t, lambda, a square over g, partial v by partial x. So those two terms here, this now, we look to those two terms, and we know in advance from mathematics that if h equal function of h x of t, function of x and t, and if v is function of x and t, then the total derivative, I have an equation of total derivative, which is called dh by dt equal partial h by partial t plus partial h by partial x dx by dt. Similarly, dv by dt, partial v by partial t, partial v by partial x dx by dt. I guess we took that expression 2 years ago from in your studies, okay? So why I put this form here? I just want you to show the imitation between this term and this term, and also about this brackets and this term here. What I have to learn here? What I have to learn here is that this partial h by partial t, I have it here. Partial h by partial x, I have it here. This is multiplied by dx by dt. So if this part here, g over lambda, is equal to dx by dt, I can take all these brackets and put dh by dt. Again, if I look to the other brackets, partial v by partial t, partial v by partial t, partial v by partial x, partial v by partial x. But I have a term here called lambda a square over g, and I have a term called dx by dt. So if this term lambda a square over g equal to dx by dt, I can take all that and call it dv by dt. So now I have a very nice things to be done. If I say the g over lambda here and the lambda a square over g, which is here, g over lambda a square over g, if I equate them with dx by dt, everything will be super now. Why? Because if this condition is valid, if this condition which I wrote down here is valid, it means that I can take out the first bracket and put dh by dt instead. And also I can take out this bracket, second bracket here, and put dv by dt instead. And this is what I have done here. I have take out this one, I have take out this one, and arrange. Except that there is something here I have to say. If I say that g over lambda equal dx over dt equal to lambda a square over g, I have something here. If I multiply those two, forget about the middle one. If I multiply the g by g, which is g squared, and lambda a squared by lambda, it would be lambda square a squared. So it means that lambda, it will be equal plus or minus g over a. So in another word, I can use this equation. First, I use them to switch the partial derivative form into a total derivative.